Hello everyone. I'm Shuji Wan from Tianjin Normal University. Today, I'm going to share our team's research in ICCV 2025, titled Monocular Semantic Scene Completion via Masked Recurrent Networks. My collaborators include Xinran Wu from Tianjin Normal University, Song Wang from Zhejiang University, Lingdong Kong from the National University of Singapore, and Ziping Zhao from Tianjin Normal University. Now, let's begin the introduction to this research. First, let's understand the motivation behind this study. Current monocular semantic scene completion methods mostly adopt a single-stage framework, whose goal is to simultaneously accomplish two tasks: visible region segmentation and occluded region completion. This leads to high coupling between the segmentation and completion tasks and poor performance in complex scenes. To overcome the limitations of existing methods, we propose a two-stage framework named Monocular Masked Recurrent Network. The first stage is coarse monocular semantic scene completion and the second stage is the masked recurrent network. The core advantages of MonoMRN stem from two key components. First, the masked sparse-gated recurrent unit, which iteratively refines features through continuous updates, thereby reducing computational cost and improving performance by focusing only on occupied regions with the mask updating module. Second, the proposed distance attention projection serves as the input to the masked sparse-gated recurrent unit and effectively reduces projection errors, further enhancing the accuracy of feature updates. MonoMRN starts with a single RGB image, which is encoded by a 2D network. The extracted features are projected into 3D using estimated depth, then processed by a lightweight 3D network to produce coarse MSSC results and an initial mask. In the second stage, the masked recurrent network refines these outputs, taking the coarse features, initial mask, and DAP features. It iteratively updates them via MSGRU, improving voxel occupancy and semantic labels in each iteration. The first stage, coarse MSSC, consists of three steps. 1. 2D feature learning, where RGB features in depth are extracted from the input image. 2. 2D 3D projection, which maps the 2D features into 3D space using the depth and camera parameters, and 3. 3D network processing, where the projected 3D features are used to generate coarse MSSC results and an initial mask. The core of the second stage is the masked sparse-gated recurrent unit, MSGRU, which efficiently refines 3D features by focusing only on occupied voxels and using sparse convolutions. MSGRU has two key components: distance attention projection. It improves feature projection to 3D by assigning higher attention weights to voxels near observed surfaces and lower weights to farther voxels, balancing coverage and accuracy while avoiding excessive errors in occluded regions. Mask updating module. This module updates the occupancy mask iteratively to reduce interference with MSSC prediction. It processes features from the MSSC head, applies convolution, pooling, dropout, and softmax operations, then updates the mask by adding top K occupied voxels and removing top K empty voxels, improving mask accuracy each iteration. To train MonoMRN, we employ three losses: the sequential MSSC loss for supervising coarse and recurrent predictions, the sequential mask loss for guiding mask prediction to accurately identify occupied regions, and the scene class affinity loss. Next are the quantitative results on the NYUV2 dataset. On the NYUV2 dataset, MonoMRN achieves state-of-the-art performance with an SCIOU of 53.16% and an SSCMIOU of 30.73%. On the Semantic Kitty dataset, MonoMRN surpasses prior methods with an SCIOU of 42% and an SSCMIOU of 13.8%, demonstrating strong generalization and competitiveness. Now, let's look at the visualization results, starting with the qualitative comparison on the NYUV2 dataset. The slide shows 5 groups of results: RGB input, ground truth, GT, the existing SOTA method monoscene, our baseline model, and MonoMRN. It can be seen that MonoMRN restores more detailed features, for example, in categories such as ceiling, window, and chair. The results of MonoMRN are closer to the ground truth than those of monoscene and the baseline model. This proves that our two-stage framework and core components are highly effective in indoor scene completion. This slide shows the outputs of MonoMRN at different stages, allowing us to intuitively observe the refinement process. From left to right, they are RGB input, ground truth, coarse estimation, results after 1 iteration, and results after 2 iterations. The coarse estimation is relatively rough and lacks a large number of details. The results after 1 iteration are significantly improved, with more voxels correctly labeled. The results after 2 iterations are even closer to the ground truth. This indicates that the masked recurrent network can gradually optimize the course results, and 2 iterations are sufficient to achieve good performance. Interferences are inevitable in real-world scenes, so we tested the robustness of MonoMRN. We simulated 4 interference scenarios: indoor dark conditions, indoor motion blur, outdoor brightness conditions, and outdoor fog conditions. The chart compares the performance with and without the masked recurrent network, MRN. Obviously, under all interference scenarios, both the SCIOU and SSCMIOU are higher when MRN is added. This proves that MRN makes MonoMRN more resistant to noise in real-world scenes. In summary, we present MonoMRN, a 2-stage framework for monocular semantic scene completion. By breaking the task into coarse MSSC and masked recurrent refinement, and leveraging key components such as MSGRU, distance attention projection, and the mask updating module, MonoMRN achieves state-of-the-art results on both NYUV2 and Semantic Kitty, while showing strong robustness under challenging conditions. I'm happy to answer any questions or discuss the work further. Please feel free to reach out to me via email.